This is your presenter Asloob Mudassar, and I am presenting slide number 55 of the course on laser physics. Question is, find an expression for the radiated power due to spontaneous emission when both the radiative and non-radiative processes are occurring. How can the overall lifetime tau due to both the processes and the radiative lifetime tau are be determined? The answer is, considering a two-level system, let N2 is the population per unit volume of the upper level at time t in the presence of both the radiative and non-radiative processes. The equation of rate of decay of the population of level 2 can be written as dN2 over dt is equal to minus N2 over minus, within the parentheses we have N2 over tau r plus N2 over tau nr, because we have included both the processes. So we have, if we write them separately, we have a minus N2 over tau r and minus N2 over tau nr. And on the right hand side we have written it as equal to N2 over tau, where tau is the now can be written as 1 over tau is equal to 1 over tau r plus 1 over tau nr. So we have included both the processes, where tau r and tau nr are the lifetimes due to radiative and non-radiative processes respectively. The solution of equation 55.1 gives. So this is the solution. N2 of t is equal to N2 of 0 multiplied by e to the power minus t over tau, as shown in equation number 2, where N2 of 0 is the population of level 2 at time t is equal to 0. Let nu naught is the transition frequency in the radiated decay process. The spontaneously emitted power is then given by P of t is equal to 1 over tau nr multiplied, within the parentheses we have N2 of t multiplied by a total volume of the material multiplied by h nu naught. And then on the right hand side we have substituted the value of N2 t from equation number 2, and then we have written the expanded form of the version as 1 over tau r multiplied, within the parentheses we have N2 of 0 multiplied by volume multiplied by e to the power minus t over tau, and at the end we have h nu naught. So if you consider this formula, N2 of t is actually the volume, is actually the population of the volume, is the population at level 2 per unit volume. So we are multiplying it with the total volume so that it becomes the total number of total number of species present in level 2. And h nu naught is the energy of each photon. So that becomes, so that gives you the total energy, and then you see that the total energy divided by the tau or time, we have the dimensions of power. So that's why we have P of t is written in terms of the right hand side quantities of equation number 3, where V is the volume of the material. By monitoring the decay of spontaneously emitted light from a sample, one can measure the overall lifetime tau. To determine tau r, it is first required to determine the fluorescence quantum field phi, defined as, so phi, the quantum field, the quantum yield phi is defined as phi is equal to number of emitted photons divided by the number of atoms initially at level 2. The mathematical form of phi is given by phi is equal to integral of P of t divided by h nu naught, and then whole multiplied with the dt, and divided by N2 of 0 and multiplied with the volume. You see that P of t divided by h nu naught will give you the total energy, will give you the energy at time t. And then we are integrating with respect to dt, it means that we are summing up the total energy. So the numerator gives you the total energy in the level 2. and we are dividing it with the N2 of 0 multiplied by V, which gives you the total number of which gives the population of the level 2. So in this way you get the quantum yield phi. Numerator and denominator are determined separately, and thus phi is known. Phi can also be defined using equation 55.3. That is this equation. So we can write phi is equal to tau over tau r. Since phi and tau are known in this equation, two quantities are known. One is phi and the other is tau. We have described the method written in blue that how we can determine the value of tau. So since phi and tau are known, tau r can be calculated. The transition rate in non-radiative decay without collision depends on the distance of the donor to acceptor, which may be random or fixed as in solids or varies slowly as in liquids. The overall decay then shows exponential behavior and can be written in the following form. So we have, you see that we have written N2 as a function of time earlier, for example in equation number 2, that is n of t, N2 of t is equal to N2 of 0 e to the power minus t over tau. Now we have included both processes, that is the radiative and non-radiative decay, and due to that one we have N2 of tau, N2 of t is equal to N2 of 0 and then multiplied by the exponential raised to the power minus, within the parentheses we have t over tau r plus c into t raised to the power half. The constant c present in the exponent is proportional to acceptor concentration. Using equation 55.6 instead of 55.2, the radiated power P of t is determined. You see that in this formula where the this is the P of t is the radiated power spontaneously emitted. You see that in this formula we have plugged in the value of N2 of t from equation number 2, because it involves only one process. But if we want to include both the processes, that is the radiative and non-radiative decay processes, we have to replace N2 of t using equation number 6, which is given over here. That is N2 of t is equal to N2 of 0 multiplied by e to the power minus, within parentheses we have t over tau r plus c into t raised to power half. So using this value of N2 of t in this equation, we can determine the spontaneously emitted power due to two processes, that is the radiative processes and the non-radiative processes. So this is the end of slide number 55.